we recall the important characteristic of an LTI system is that it is fully characterized by its impulse response. And here we want to reframe that based on the action of sinusoids, which we call the frequency response. And what this will really tell us is that the output of the frequency response given an input sinusoid is a sinusoid again with the same frequency, but with a different magnitude and phase. Or you can interpret that as a different complex amplitude. And as a sort of additional note on other connections inside this class is that almost all periodic signals can be characterized by its Fourier series. And this really tells us that no matter what signal you have, as long as it's periodic, then you can characterize it by its frequency response and a result which is almost identical to the impulse response. To remind you of what the frequency response does to a signal, let's say that we have a signal here, complex sinusoid x of n equals a e to the j phi, e to the j omega naught n. And here is your frequency response, h e to the j omega naught, omega hat. And what this will do essentially is it's going to split into two parts because it's a complex term. It has a magnitude term, which we'll call also the gain, the absolute value of h e to the j omega hat. And it also has the angular term, the phase response term. And what you'll see a lot in class is that you physically graph those depending on what you have. And let's say this is your magnitude response here, and this is your phase response. And it's going to look different for many different examples. And it's a continuous graph relative to your input signal, which is discrete. And the sort of idea is that you want to use the property of superposition. And the superposition principle states that practically you only need to multiply element-wise the elements of x at the same frequency as corresponding to the same frequencies of the frequency response. So in this example, what I might say is I have a signal x of n equals a e to the j0, which is the zeroth DC term. You have a term at the omega 1 frequency, omega 2 frequency, and you minus some phase shift terms, which don't do too much. And it basically says, hey, just take the value of h e to the j0, at let's say 0 here, 0 here, and you do the same thing for different omega 1, omega 2, and you just multiply the same part. There are no cross terms that happen when you do this multiplication. So different frequencies do not interact with each other. You've sort of done this in class as a classwork example, and what you're given is, hey, I have a signal, complex sinusoid consisting of a pi over 2 term and a pi over 4 term, and you also have a frequency response that's also associated with the pi over 2 frequency and pi over 4 frequency. And the result here that you should have gotten is that the output of this process is going to be the element-wise multiplication of the identical frequency terms. So that was the easy result that you got here.